So let's get started with day 2. If today is your first day with us, I want to say welcome. You can check out what happened on the first day by using an interactive video lesson, which is available on the course webpage, which is listed here. You can also get to that through your menu if you choose, click the 3 lines here. And then again, the course homepage for the actively selected course is going to be listed there. So you can always get to that way. And we're going to have these interactive lessons available for each day. So you'll always be able to see the video and also work through the messages, answer questions and stuff as you go for each day. I probably will not edit the video as much as I did the first day. So I edited it down from about 65 minutes down to about 45 minutes just by cutting out the ums and various sort of spaces of dead time that you can kind of generate yourself by pausing the video when you go through it asynchronously. But in any case, that will continue to be available. I'll try to always post those day of. Sometimes it might be next day. So before we get started with the new content, picking up where we left off from last time, I'd like to do a peer review question to start out, to do a bit of review and to practice the peer review questions a bit more. So remember, the way that this works is that I'll ask you a question and then you answer. And then after you answer, you should receive a reply, an answer from another student who answered around the same time as you, and then you'll have a chance to respond to that student if you want to. And I think the main part of this that warrants explanation, although we discussed it last time as well, is that only your next message. So I didn't want to introduce separate components to the interface. So when you get a peer response, your next message will be sent to that person. And this is broken up by either a non-private instructor message continuing to move class forward, or if you send a message. So if you really want to send a message to me, just send something to the peer, and then you're back to messaging the central classroom. So the idea is just giving feedback to each other. I don't want to spawn whole new conversations because we want to keep things focused, but in any case, so let's practice that. So here's a question, 60 seconds. I'll give you to type up an answer. So in R, what is the workspace? Okay, so there were a few, as I let folks finish up their peer responses, there are a few classes of answers represented here. So there's the correct answer, which is the collection of all variable names and associated objects that have been defined by the user in the current session. There's an almost correct answer that several folks had, which is the set of all objects available in the current session. That isn't quite true because built-in objects aren't listed in the workspace. They only want to show you the new things that you created instead of the huge list of things which would be available straight from the beginning without you having typed anything. There's another class of answer, which I think is a completely reasonable guess about what the term workspace would mean, which happens to be incorrect in the context of R because workspace is a term of art with a specific meaning. But people were alluding to the class of things that RStudio and Jupyter are examples of, which is to say the place where you enter your code and see things come back from the interpreter, maybe open up a CSV file and look at some data, that sort of thing. That is we would call that an integrated development environment, or IDE. So that's a different thing than a workspace. Okay, so just to close the loop on that, a workspace is a collection of all user-defined variable names and their associated values. So the objects associated with them through whatever assignment operations have been performed. Okay, just one more peer question to get things going, and then we'll step into the new content. So write a line of R code which will tell you which power of 2 is equal to 8192. Some creative solutions here. Most people interpreted the question as intended, but some folks answered correctly, but through some other means. So there is one question here that I want to address for everyone in case you like this sort of thing. So there are styling options available in Prismia. They're just hidden. So I didn't want to put a bunch of buttons there for you to click, but you can access lots of stuff. Like you can put things in italics by putting asterisks around them. So asterisk and then the name and then another asterisk. You want to have some code. You can put backticks around it, and then when you hit the space bar, it will be formatted. If you want to put a whole code block, you can do 3 backticks and then hit the space bar, and then you can type your code here, and it looks like code instead of regular text. One thing about that though is you often need to put new lines, and if you hit enter, it will send the message. So you have to do shift enter to get a new line if you do it that way. In any case, lots of folks are on point here. So you can do log 8192 comma 2 or log 8192 comma base equals 2. Okay, so let's continue with content from the book. So we'll kind of get back into the mainstream of the narrative here. All right, so this is where we left off in the book. So data types. So variables in R can have different types. So for example, we need to distinguish numbers from what are called in other languages strings, and are called somewhat confusingly in R characters, which is to say textual data. So when we put a quotation mark and then type some letters and then a close quotation mark, that's a string or a character. And that's different from a number. The computer needs to represent those two types of data in different ways, interact with them in different ways. So just like in real life, when the distinction between a food and a country is a big deal, just in the same way in programming languages, the difference between different types of objects is important and needs to be inspectable within the language. So the way that you inspect a type in R is through a function called class. So for example, if we assign the value 2 to the variable a and then ask what the class of a is, we'll be informed that it's a numeric variable. So that's telling us that 2 is of type numeric or of class numeric. So this will be a helpful tool if you're dealing with objects and you have to think, wait a minute, I don't know what type of object this is, and that's making it difficult for me to understand this particular thing. You can use this class function just interactively and ask quickly, hey, what kind of object is this? And that might help get you on the right track. So up to now, the variables we've defined have been just numbers. So this is pretty plain. We want to expand our palette somewhat. And the next example we'll give here, it's sort of stepping up in complexity. On the other hand, in a statistics context, this is a very natural thing to introduce at an early stage, namely a data frame. So the idea of a data frame is just a table. So that you want to think of this as what you would store in a spreadsheet in Excel, something like that. So the specific way in which we want to assign meaning to the way the table is laid out is by putting observations in rows and having columns correspond to variables. And it needs to be clarified here that the term variable we've now used in 2 different senses. When we assigned the value 2 to a, we called a variable up here. And that's variable in the programming sense. So that's a name that we're assigning an object to. However, in statistics, we often use the term variable to mean just some attribute whose value we either observe or intend to predict, something like that. So the example I like to keep in mind when I'm thinking about this question of the distinction between rows and columns, in other words, observations and variables, is that of patient data. So if we have some patients coming into a clinic and we record information about those patients' vitals in a table, we're going to put them in rows specifically. Of course, you could do it the other way, but this is the convention that has been widely adopted throughout statistical computing. So we're going to record the patient's vitals in rows. That way, each row corresponds to an observation, in other words, a patient, and each column corresponds to a variable, in other words, a piece of medical data like that patient's blood pressure or weight or height or name, or some categorical information about that particular patient. So this is really a big chunk of modern data analysis. This is going to involve pulling in data specifically in the form of a data frame and then doing various things with that data. So for example, let's pull in the murders data set from the DS Labs package. So we'll need to install that package because, as we discussed last time, these code cells are ephemeral, so installing the package last time won't actually install it this time. So the way this works is a little bit non-standard. I'm going to walk you through this. So this part is fine. So this install.packages is a function that installs packages, as the name suggests. We tell it we want the DS Labs package. So that's a package specific to this course, or rather to the book that we're using. So the course that the book was written alongside. So we're pulling that in. That's going to have data relevant to this particular book. And then we're actually pulling it into our session here. So install.packages just installs it on your system on the hard drive. But here we're actually pulling it into our session. And then we have to use the data function to bring the murders data set into scope, bring it into our session so that we can actually use it. They could have elected to make that data set available immediately once you load the library, but you can also choose to make the user pull it in deliberately when they want to, and that's what's done here. So once we pull that data set in, we can check its class and see that it is indeed a data frame. So the name of the data frame type in R is data.frame. And remember, as we discussed last time, this dot is just another letter from R's point of view. So this is just a separator. So this is the type of a data frame in R. But of course, you want to know more about this data frame than just what's its type. And a good function for taking that next step is the str function. So you might think this means string if you're used to Python, but it means a structure. So it's helping us find out more about the structure of the object. So it's telling us, okay, we have a data frame here. It's got 51 observations and 5 variables. And we'll see why this $sign is what prints out in a little bit, but this $sign is telling us that state is going to be one of the variables, and it's giving us some example values for the state variable. So for example, Alabama is going to be in there, Alaska, and so on. The abbreviation column, likewise, you can see it's just the ordinary 2 letters abbreviation of each state. The region here, it's going to be either northeast or south, or maybe some other stuff. That's what the dots mean. And what is this word factor? We're going to have to investigate that. We'll unpack that a little bit. Population is a numeric variable. Here its first few values, and then total number of gun-related homicides is going to be in this last column here. Yeah, so there's a couple of questions that I want to handle before moving on. So observations and variables in statistics, are they synonymous to records and fields in the database world? And I would say yes, that's right. And a Prismia question, if I type a line of code in the pop-up R code cell, does it appear to instructor? And the answer is no, that's private to you. So only messages that you actually send get sent to the central classroom. You can also make a private permanent note by doing \note tab and getting this thing. And so I sent that as a student. This view that you're looking at is my student view, and that message did not arrive to the central classroom. So that's how that works. Okay, so yeah, so the structure command tells us a lot more detail about the object, so that's helpful. You might also want to look at it as a table. It is a data structure which is designed to store tabular data. So here we go, and you'll see that it's formatted nicely for us with these alternating colors and stuff. So this is taking advantage of the fact that it knows the structure and what kind of data it's supposed to represent when it displays it to you. And another handy function for kind of keeping things tidy is the head function. So head will print out the first few rows of the data frame. The idea is we don't need to see every single row. We're not visually inspecting it for something comprehensive. We just want to see kind of what it looks like. And so what we see here is that the variable names are here across the top in this header position. In the next row, we have the types. So this is telling us this column is a factor column, this column. So DBL means double, which is another term for numeric. So this is saying this is a numeric column. These are both numeric columns. This is a column of strings, or in our parlance, characters, likewise here. So, and then the rows are nicely numbered for us. That's not part of the data frame. It's just there for the visual presentation so we can see which rows are which. Okay, so in this data set, back to the observation and variable terminology. So each state is an observation and it has various pieces of data associated with it. Those pieces of data are called variables. So the state, abbreviation, region, population, and total, those are the variables of this data set. Okay, so before we proceed with answering the original question, let's talk about the various components here. So the elements that we'll need to interact in a rich way with these data frame objects. So one of the most basic things you're going to want to do in manipulating data frames is extracting a column from that data frame. And in R, the way you do this is with the $sign. So this is called the $sign accessor. And you can see that if we do murders $sign population, we're going to get the population column. So we get all the values in the population column. So one important fact here, and I think this is what you would expect, but it's going to come up actually quite a lot. So it's important to emphasize the order of the entries in this we'll see that it's a vector, but the order of entries in this column, it does preserve the order of the rows. So nothing gets scrambled here. It's not just giving you the values. It gives you the values back in the same order. And it's going to be important when we start to perform operations which involve combining columns. So we'll take advantage of the fact that they are aligned. Okay, so now we can get into talking about some of these other types. So as I alluded to a moment ago, the column here is a new kind of type to us. So it's called a vector. So a vector is a collection of objects that have the same type. So in this case, these population values, they're all numeric, and we have a bunch of them. They're in a specific order. We call that a vector. So in some sense, you can introduce the mathematical concept of vectors as simply as a starting point. At least you can describe it as just a column in a data frame. These are close to synonymous concepts at this level. And we can ascertain how many entries a vector has, in other words, how long the data frame is, by using the length function. So if we store the population column in a vector called pop, or sorry, in a variable called pop, then we can ask what length of pop is. And it's 51. So there are apparently 51 states in this data frame, which of course is telling you that the term state is being used somewhat flexibly. Of course, DC isn't there, but that makes sense if you're talking about something like gun homicides. There's no reason to exclude DC just because it's not a state. So an interesting, at least to me, kind of interesting point is that the class function doesn't actually tell you that pop is a vector. It goes straight to the type of the elements in the vector pop. So it sees that pop is a vector, and it's like, okay, well, person probably already knows it's a vector. I'm just going to tell them what kind of stuff is in the vector. So this is a numeric vector as indicated by the output of the class function. So a key point about vectors, which is going to distinguish them from another data structure we'll introduce soon, is that vectors have to have all of the values in a vector have to have the same type. So for example, in a numeric vector, every entry must be a number. So if we want to store character strings, then every entry in that vector will have to be a character string. So as an example of this, you can look at the state column. So of course that stores character strings because names of states are characters. And the class function reflects that information as we would expect. All right, so again, all the values have to be the same type. So another important type of vector another important type in R, and in particular, therefore it can be a vector type, is what's called in other languages a Boolean. In R, it's called a logical. So if we ask R, is 3 equal to 2? Then, of course, the answer is no, but it represents this sort of yes, no, true, false type value as its own data type. So it's not co-opting some other data type or representing it with a character or something like that. These are really important core values, so they get their own dedicated type, which is called a logical. So when we say is 3 equal to 2, it is not, so that resolves to false. Notice that false is all caps here, so that's important. It's case sensitive, so if you get this wrong, then it won't recognize what you're saying. Different languages use different conventions for how they capitalize these logical, they're called literals. So if you want to type it directly, literally in your code, you need to type it out like this. So one note about this operator that we just introduced here, this double equal sign. So this is what's called a relational operator, and it's just saying, are the two sides equal? And you might be used to using an equal sign for that, but it's important to use two equal signs because the single equal sign works for assignment. So if we try to say 2 equals 3, for example, here, we get an error because 2 is not a variable name that we can assign to. If we want to ask the question we really intend here, we need the double equals. So other relational operators are the ones you might expect from experience with other languages. So you can check if one number is greater than another or less than another. Similarly, less than or equal to or greater than or equal to. So this one at least kind of looks like an arrow, but it means less than or equal to. And then not equal to is the exclamation point followed by the equal sign. So if we ask is 2 unequal to 3, the answer is yes, so we get a true there. If we ask is 3 less than or equal to 3, likewise, that's also true. So relational operators come up a lot. It's important to be fluent with them because there are many use cases where they'll emerge very naturally as we're manipulating data frames. Yes, this is a good point. I told you last time assignment is the arrow. So, but in fact, the equal sign can also be used. It's just recommended to use the other one. Okay, so there are a few questions there, but I think I will answer those later. Okay, so I want to make one kind of more advanced point here because you will encounter it at some point, and if you're used to behavior from other languages, it will be confusing at first. And we can head that off now. So the values in the population figures in this table are integers. They're whole numbers that have no fractional part. And R does have an integer class that you can use that is separate from the numeric class and only handles integers. However, by default, numbers are assigned the numeric class even if they're integers. So for example, if you just type 1, you would think that would be an integer type, but in fact it's not. It's a numeric type. R is basically prepared to let that number interact with other numeric values which may not be integers and not have to change the type at all. So there are a couple of ways to convert a numeric whole number value to a number which is stored internally as an integer. So one is to use the as.integer function, or you can just append an L. And this looks kind of funky, but this is kind of hard-coded into the language. When it looks at your code, it's like, hey, did this person put an L immediately after they typed in an integer literal? If so, let's actually represent that as an integer. So if you do 1L, then it tells you that that is indeed an integer. And I think this L here is for long, which is it's a bit archaic, but It's kind of, it's an old school way of referring to an integer in computer speak. But anyway, just be aware of that distinction if that comes up. R likes to treat integer values and floats the same way with the same type called numeric. You have to kind of pull it out of that. Incidentally, just continuing this aside, and then we'll be done with it. The behavior of R in this way is somewhere in between JavaScript, which actually has no integer type at all, so everything has the same type as R's numeric type, and Python or Julia, which do make that distinction between floats and integers by default. So it's kind of sitting somewhere in between there. Yeah. So here's a question adjacent to that, which I think it's a great question because it helps clarify what I'm saying here and maybe why R would adopt the convention that it does. So suppose that you're pulling in data from some source and you're the R programming environment, you're pulling in data from some source and you need to decide what type of column should be. So it in fact is no problem at all if you have integers and decimals mixed in the same column, because R was going to treat them all as decimals anyway. It assumes they're all numeric values. Even if they all end up being integers, doesn't care, they're just going to be numerics. Whereas if you had a language that distinguishes integers and decimals, you might have to do something like, as you're reading the data in, if they're all integers, you might say, okay, well, I'm going to make this an integer column. And then all of a sudden you run into a 2.5 and you're like, uh-oh, that's not going to work. I'm going to have to go back and change the type and switch all of these to being floating point numeric values instead of ordinary integers. Yeah, so it isn't a problem because R treated the integers the same as the non-integer values anyway. All right, so we've tackled now a few of the types that we've seen. So character strings and numeric values. There's another one that we saw when we looked at this murders data set that warrants some explanation as well. So this is called a factor. So when we assign each state to a region, that's categorical information. So the Massachusetts is a state in the Northeast, and Washington is a state in the Northwest. So this is categorical information that there's a limited number of potential values that each state could have, and we just need to say which state has which values. So in other languages, this might be called a categorical variable. In R, it's called a factor, just a different terminology. There are lots of reasons why you might want to store this data in its own way and distinguish it. Here's one convenient thing about factors. So factor variables know what possible values they can have. So when we say, murders $region, so we're pulling out the region column from the murders data set, it knows that this is a factor, and so our environment knows that this is a factor, and in that factor are stored the levels or possible values that factor can take on, and we can pull them out with the levels function. And that's helpful because that way you don't have to try to recover that information somehow from the data frame. Maybe it's really big and it would take a long time. It could be wasteful. It's nice to just have that information handy to just grab. So, it is a meaningful question. What are the different regions in the United States? There's no canonical way to do this. And in fact, I would object to this one personally because I'm from Mississippi and the Southeast is not the same as the Southwest. So I think you need at least one more here. But in any case, yeah, this is definitely north bias. So you've got Northeast, North Central, and then just West. That one's also a bit reductive, perhaps. In any case, the point is you can see all of the possible values using the levels function and just extract them from that factor column. So one kind of detailed point about what's going on here is that R is storing these levels as integer values. So the actual column, all 51 values that get stored, it's not repeating these character strings over and over again. It's not saying Northeast, Northeast, Northeast for each Northeastern state. It's just indexing this one as 1 and then storing a 1 value there. So when it actually prints, when we look at the murders data set like this, and it's actually printing the value here, it has to go sort of pull that out from where the levels are stored in order to display it here. Because what's actually stored, as you might remember when we called this function, what's actually stored is numbers. So that's visible here. So like south is in the position number 2, and the very first entry of the data frame has a 2 here. So that's saying that the first state, which is Alabama, is a southern state, and that's accurate. So you can kind of see a little bit through this structure function how this is looking under the hood for these factors. Yeah, so a couple of comments. So it's less memory to store a single number per row. That's right. It costs a lot of memory potentially if you have a really big data frame to have to write the entire character string northeast over and over again every time there's a northeastern state, and just instead of just putting a 1 there. And of course, it's completely cheap to just store these 4 character strings in an sort of auxiliary, sort of store them to the side where you can reach in and grab that information when you need it, but not have to repeat it all the way down the whole data frame. Okay, so yeah, this is a good question. So if you have a column that's, say, a character string, if you have a column that's, say, a character string, but you want to know how many unique values they are. So in other words, R didn't do the work of turning that into a factor column for you, but you want to, in some ways, treat it as a factor column. Yeah, so we'll get to that. That's a good question. Yeah, this is an operation that comes up a lot, though. So a little bit more about the factors. The levels have an order of appearance that may be different from the way they appear in the data frame. So in R, the default is to just put the factors in alphabetical order. However, there's sometimes a natural order based on the interpretation that you're giving to the different values that the factor can take on. That might make it more reasonable to use a different order. For example, with geographic regions, you might sort of loosely proceed west to east or something like that. And you can specify an order with the levels argument when you create the factor. So you can create a factor directly, and you can tell it how you want the levels to look when you do that. So I'll show you, we didn't create this one, but I'll show you how to change it. So the function reorder lets us go back and change the order of a factor that we already have. So for example, suppose that we want to order the levels of the region by the total number of murders rather than alphabetical order. So we need to use the murders total vector and somehow come up with this information. So there are really kind of a couple of things that need to happen here. One is we need to somehow use the data frame. So remember, this is what the data frame looks like. We don't have the total number of gun-related homicides for each region. We just have them for each state, and we have the regions for each state. So this is some information we're going to have to extract. And I'll show you. I think this may be a little more difficult to conceptualize than it's sometimes given credit for. So I'll show you a little animated GIF to help you visualize what's happening here. So you'll notice that we started with just a plain data frame like our original one looked, and then we grouped by region. So we put, and of course only have a few of them here to keep the visualization small, but we put all the western states together, all the southern states together, all the northeastern states together, and then we just sum within each group. So all the southern states are going to get added together, all the western states are going to get added together, and that's the value you see here in this sum column up at the top with each of these groups. So the reorder function will let us kind of avoid having to do that work. We'll just tell the reorder function where to look to do that work, and it will do it for us. All right, so here's the code that will do this. So this is the magic is right here. So we'll just define region and value to be the region column, and then the total number of murders column, and then we'll say what we want to do here is take the region factor and reorder it based on the values in the value column. And the function that should be used to aggregate or pull together all of these values that it's going to get within each group is the sum function. So it should add, which is exactly what we saw here in this visualization. So this is kind of, the reorder function is doing a lot of heavy lifting for us. All we need to do is tell it what column to look at for the numbers to perform this ordering, and how to perform this aggregation within each group that it gets when it groups by this factor column. Right, and once we have that reordered factor, we can write over the region object, which we originally defined here. So we're reordering it, but that doesn't change the original. In order to change this value of this variable, we have to assign to it here. All right, so we get this new ordering, and this is the right thing. So the Northeast has the fewest and the South has the most. This is the correct order. So this reorder operation worked. So this is a bit of a preview. This operation that we did where we group and then aggregate, there are going to be a lot of operations of that general class that we'll learn to be facile with, and that'll allow us to access a wide range of different operations that we're going to need to perform. But this is a specific context that's sort of pointing the way towards that. So one point of caution here is that factors behave like characters in some ways and in other ways not. So keeping it straight which columns are actually factors and which columns are characters is important. If you get them mixed up, then you can pretty easily run into bugs in R. So this is something to be aware of from the beginning. So factors and characters are really not the same, but close enough to confuse you. Okay, so I'm going to mention another R data type that tends to get a little bit short shrift, but I think it's helpful, partially because it comes up sometimes and partly because it is closely connected to data frames, and that can help clarify why data frames work the way they do. So this type is called a list, and lists are useful because you can store lots of different types. So with vectors, you only store values of the same type, whereas sometimes you really do want to store different types. For example, a student's name might be John Doe, their student ID, some grades they made on various assignments, and then their final grade. These are all different types. This is a character, this is a numeric, this is a vector of numerics, and well, this is a character as well. But we couldn't store this in a vector. We have to store it in something that's capable of handling different types, and in R, that the built-in type that is used for that is list. So we define a list by just using the list function and then supplying the named arguments however we want. So we'll say what we're going to call that particular entry, as well as the value for that particular entry. And we can ask what kind of thing that is, and R will tell us that indeed it is a list. So this is its own type. And you can extract the components of a list using the $ accessor, just like with a data frame. So this is the sense in which this is very closely related to a data frame. A data frame is essentially just kind of pulling together different columns. Likewise, a list is just pulling together different values into the same object. So we can say for this particular student, what's their student ID? And we get 1, 2, 3, 4, which is what we put in. So a couple of questions that I've gotten recently that I want to answer is they're good questions that tie into the topics here in a nice way. So can the reorder function be used to implement something like a pivot table from Excel? So we'll see how to achieve that kind of functionality directly. So reorder is doing it for us as a convenience. So we'll want to use types. I forgot to clear the message again, so you have this blank cell. But anyway, we'll want to use functions that are designed specifically for this task rather than functions that are designed for some other task that will do this aggregation step for us, this grouping and aggregation step for us. But yeah, you can certainly achieve that goal, and it's going to be important to be able to do those kinds of operations efficiently. Yeah, so there's some questions about lists in R as related to things that you might have seen in other languages. So if you're not familiar with other languages, don't worry about this part. But yes, a list it's I would say it's most like a dictionary from Python, or in some ways like a struct from Julia or C. It's more flexible than those types in those two languages. But yeah, it's not like a Python list. If you're used to lists as specifically ordered collections of things, lists in R are sort of a hybrid of that in dictionaries. And then here's one more question about lists. So will lists repeat values? So the key point here is that, oh, sorry, I forgot to type the answer to the previous one, so it's in the transcript. So yes, R's lists are like dictionaries from Python, somewhat like structs. And then, so the list will just store exactly what you give it. So if you give it for each attribute. So if you give it a factor, it will store those values efficiently. Whereas if you give it a vector of characters, it will not. Okay, so another point about lists is that you can use the double square bracket accessor instead of the $ if you want. So that also works. And this relates to a general point, which is that there are often multiple ways of doing the same thing in R. It doesn't have a philosophy of making everything doable in the same way for everybody so that there's a lot of consistency. Rather, there should be variety so that you can adjust to your own personal taste to some extent. And also there might be some situations where like, for example, maybe you want to put a space in there instead of having an underscore, and then the $ wouldn't work anymore. But because this involves enclosing it in quotes, then it could work. So one way in which lists are not like dictionaries, if you're used to dictionaries, is that you don't need to give it names. You can actually just supply an ordered list of objects, and it will handle that just fine. So it will supply the names as just the indices 1, 2, 3, and so on for itself. And that makes it slightly more convenient if you do want to just list some things in order and not name them. That this is more convenient than having to manually supply the names 1, 2, 3, and so on. Okay, so after we create this record that has these two entries, we can access the first entry with 1 in double brackets and the second entry with 2. Okay, so lists won't come up for a while, but I mentioned them just for completeness because they can come up as you explore and encounter code in the wild. It's helpful to know about all of the basic data types. Okay, so here's yet another type. So this might seem redundant, but it's not. This is a new type. Matrices are another type of object that are, so as I said, it might seem redundant. The reason is that we've already talked about data frames, and data frames are two-dimensional tabular data structures. What's the difference between a matrix and a data frame? And the difference is that matrices are more like vectors in the sense that everything has to be the same type. So you can have a matrix of numerics, that's the most common situation. You can have a matrix of characters, a matrix of logicals, but in any case, they all have to be the same type. You can't have some numeric entries and some character entries, for example. And this means that data frames are more flexible and interesting for storing data. We can also assign names to the columns in a data frame, whereas in a matrix, there are no names. It's just a table of entries. So for that reason, you will use data frames more often. However, matrices do have one significant advantage, which makes them important as an independent type over data frames, which is that you can do matrix algebra with them. You can multiply matrices, add matrices, that kind of stuff. So we're not going to get into that. If it's unfamiliar to you, don't worry about it. But that is an important reason why matrices exist separate from data frames. If we want to define a matrix in our code, we use the matrix function. And the way this works is that we supply the entries as a vector. So other languages, if you're familiar with Julia, for example, have a very nice syntax for directly typing in a matrix into your program. R does not. So you have to tell it all of the entries that you want in order, and then use the matrix function to reshape that vector of entries into a matrix. So for example, we'll get to this particular piece of syntax later, but as you might guess, it means all the numbers from 1 to 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we reshape that into a 4x3 matrix. So this matrix has 4 rows and 3 columns, and it took the entries 1 through 12 and it positioned them into that matrix. And you might have imagined it would go the other way, that it would do 1, 2, 3, 4, 5, 6 like that, but it's column wise. So this is called a column major matrix, where the idea is that if you want to enumerate the entries of the matrix, you want to go down columns first. So you start top left, of course, but then instead of proceeding to the right, you're going to proceed down. And then when you get to the end of that one, you're going to come back to the top. So yes, so that's an important point. Also, picking back up this question, yes, indices in R start at 1, not 0. Okay, so if you want to access particular entries in a matrix, you can use square brackets. So for example, if you want the second row, third column entry, you can just do 2, 3 like that. And if you want to grab a whole row, you can just leave the corresponding entry blank. So if we want the second row, we say second row, comma, and then instead of specifying a column number, we just leave it just a space, or doesn't even have to be a space there. Just be like that. And that gives us the whole second row. So 2, 6, 10, so that makes sense. And when you slice a matrix in this way, extracting a particular row or column, what you get is a vector, not another matrix. So you might have noticed that the way that these cells output vectors is they put these central dots in between the entries of the vector. And the way it outputs a matrix is it actually prints it in this pretty way. So you can tell from that what we got here is a matrix rather than, sorry, a vector rather than a matrix. Right, and that works the other way too. If we want a whole column, we say nothing for the row and then 3 for the column. And that'll grab the whole third column, as you see here. So you can also get more than one row or column at a time. So for example, if we wanted to grab the second and third column, then we can do 2, 3 like this. And that gets the second and third column. And you'll see that that actually does give a matrix. I mean, it has to, so it does. And you can subset both. So you can pull out a submatrix by grabbing, let's say, the first and second rows and the second and third columns. And that works as you would expect. First, the top 2 really of this matrix. All right, so just a couple more points and then we're done. You can convert a matrix to a data frame if you want to by just using the as data frame function. So really any type that you might want to convert to, as dot is as dot, and then the name of that type is probably the right name for the function that does that conversion. So if you want to convert it to a data frame, we can do that. And then one final point about the intersection between matrices and data frames. So data frames do support this single bracket accessing syntax, where if you know the indices of the values you want to extract, you can use single brackets and get them this way as if it were a matrix. This sort of lets you treat a data frame like it is a matrix. And we grab, let's say, the second and third rows and all the columns, and it looks like this. Okay, so that brings us to time. If you have any follow-up questions, let me know. I'll stick around for a bit. Also, if you want to introduce yourself in chat over Zoom, I'm going to stop the recording, and I'm happy to talk to you for a few minutes. And several people asked questions throughout the lecture that I'm going to follow up with you later. So you might have, if you asked a question last time, you might have gotten a follow-up message from me. What I do is I just sweep through pick the answers. Sorry, pick out the messages that were unanswered questions, and I can respond to you, and then I trigger an email, so you don't need to come back and check for when I followed up. You'll just get an email that you'll be able to see.